Okay, so today, and also yesterday, I guess, we are starting to get some of the payoff from all the sort of technicalities that we spent the beginning half of the course on. So, assuming you're still with me at all, so we're going to start doing some, well, we're going to start doing some actual physics with the formalism of supersymmetry. And yesterday we finished by discussing the idea of dynamical SUSY breaking and the role that the Witten index plays in dynamical SUSY breaking. So just to remind you, because I said it very quickly at the end, so the Witten index is not equal to 0. If the Witten index is not equal to 0, this implies that the theory has 0 energy states. Okay, so in other words, the theory has SUSY vacuum. Okay, so the Witten index is non-zero in a given theory. That means the theory does not break supersymmetry in the ground state. Okay, and the advantage of the Witten index, the nice thing about the Witten index is, I didn't say it yesterday, is that it's a topological invariant, which means that it's just an integer. Okay, so it's invariant under any continuous deformations of the theory that aren't too violent. Okay, so if it's invariant under these continuous deformations, that means that you can calculate this even in a strongly coupled theory. Often by, if that theory has a parameter, like the coupling, even though we're interested in what it is in strong coupling limit, we can access what it is, we can calculate it in weak coupling limit, and the answer is supposed to be the same. Okay, so that's the power of this index, or indices in general, is that they can teach us things about strongly coupled theories, which otherwise we wouldn't have access to. Okay, so the application of this to dynamical SUSY breaking is that the index is equal to NC in SUNC Superyang-Mills theory. Okay, so that's, I'm going to show you how that works. This is a fact, which is that in pure Superyang-Mills theory, the Witten index is non-zero. Okay, so this theory here does not break SUSY. Okay, this theory here does not, pure Superang-Mills theory does not break supersymmetry. And so also any theory which reduces to SUNC Superang-Mills at low energies also does not break SUSY. Okay, so the picture is, if I have some theory and there's some mass scale m, say, at which I integrate out most of that theory, and then below that mass scale m, I have SUNC Superang-Mills, okay, then we've shown that this theory does not break SUSY, so this theory has, has vacua with 0 energy. Okay, so any theory that has this theory contained in it as an effective theory, okay, then will also have the 0 energy vacuum. Okay, because there's 0 energy. All right. So okay, so that pretty much rules out. So what are theories that reduce to pure Superang-Mills? That pretty much rules out any theory that has vector-like matter. Okay, vector-like matter means that, there's for every representation of SUNC, there's an opposite conjugate representation in the theory, right? So then we can add a mass term for those fields and then decouple them, right? It doesn't matter what the mass term is, as long as there is a mass term at all, right? Because then below that mass scale, you'll be back to Superang-Mills. Okay? So, all right. So in order to break, so because of this fact, any theory which reduces to Superang-Mills at low energies does not break SUSY. So we ended last lecture by saying that for ESP, we need either a chiral gauge theory, okay, a theory with chiral matter that comes in representations which can't be paired up into mass terms, okay, or a theory with massless vector matter. Okay, a theory in which there are vector-like representations, but you don't have a mass term for them for some reason. Maybe you impose another global symmetry that forbids such mass terms, for instance. Okay, so these are the two possibilities that survive this Witten index calculation of super Yang-Mills theory. Okay, are there any questions about that? Yes?
Yeah, it's like the Witten index when it's not vanishing. I mean, I was wondering if it's a double implication is if and only if.
No, so let's see. It's not a double, it's not, the implication doesn't go the other way, because if you recall, this only counts the SUSY vacuum modulo a sign. This only counts the zero energy states modulo a sign, so what we said yesterday is that this counts the number of bosonic states of zero energy minus the number of fermionic states of zero energy, right? So my theory could have some number of SUSY vacua, but that could come in pairs, just cancel each other, give me zero Witten index. So just because the Witten index is zero doesn't mean that you're done, right, if the SUSY vacua come in pairs and cancel. Yeah. But if it's non-zero, then for sure, you know, one of these two things is non-zero. You know that then, and then you're done. Okay, yeah, so the logic is a little subtle, but yeah. Are there any other questions? Okay, so so that's where we ended last time, and so there was an active field of research in the 90s primarily, looking for examples, or generating examples of dynamical SUSY breaking. So in Witten's original work, he showed that super Yang-Mills, the simplest possible SUSY gauge theory, did not do the job. And then it was an open question, are there any, what's the first, who can write down the first example of dynamical SUSY breaking? Okay, and so there was an active, so Affleck, Dine, and Seiberg were the first to write one down, and there was an active area of research, you know, generalizing on that, and looking for other mechanisms, generalizing on that. Okay, and so people focused on chiral gauge theories and massless, later massless vector-like matter theories. Okay, so here I've written a table, which I'll try not to erase, summarizing the different types of dynamical SUSY breaking models that people have come up with. And so today we're going to be going through a lightning overview of these models. And this is not doing the subject any justice at all. It's kind of unfortunate, but you know, to really do this justice would require another, or its own 10 lectures, I would say, 10 hours. Or more. So really, to understand this subject, you need to tie together a lot of physics and a lot of non-perturbative dynamics of SUSY gauge theories. Okay, which is a very interesting subject on its own right. So the best I can do for you today in 1.5 hours is to sort of highlight the basic ideas here. I won't be proving those things, okay, but I'll just be calling out a bunch of facts about SUSY gauge theories and their dynamics, and then you know, hopefully you can go and read about these things at length on your own. Okay, so consider it just like a very quick tour through this subject. Okay, so the basic fact, the basic idea when you come to look for models which break SUSY dynamically is that they are based on, so super Yang-Mills doesn't work, all right? So what's the next most complicated SUSY gauge theory? Well, if this is like the theory, this would be like QCD without any quarks, right? So let's add some quarks to the theory. So let's add some number of flavors to the theory. Okay? So to really understand dynamical SUSY breaking, one has to first understand ESB one has to first understand the dynamics, the non-perturbative dynamics of SUSY QCD. Okay? So that's the next most complicated thing after superyannuals, right? We add some flavors. So SUSY QCD, now there's different, of course, classical gauge groups, SU, SO, and SP. The simplest case is SU, so we're just going to focus on that today. And there are some additional complications for the other classical groups. So let's just focus on SU, NC. Okay, so there's some NC colors. And then the other parameter, that controls the dynamics of these theories is the number of flavors. Okay? So the dynamics or the phases of the theory depend on the number of flavors versus the number of colors. Okay? And let's keep in mind, by flavors we mean some number of quark superfields and some number of antiquark, same number of antiquark superfields. Okay, so we'll be making tables which look like this a lot. So here's the gauge group, and here are the matter fields. So we have Q chiral superfields that transform in the fundamental SUNC. Oh, sorry, we have some number of matter superfields labeled by Q, which transform in the fundamental of SUNC, and an equal number of anti-fundamentals, which we'll call Q tilde. Okay? And so these have a global symmetry associated with them. And actually, well, sorry, they have an SUNF times SUNF associated with them. Okay, and this is how we denote the fact that there are NF flavors. Okay, so this should all look very familiar to you from regular QCD, where NF is equal to 3. The only thing is here we have supersymmetrized everything. So now instead of having quarks, we have quark superfields. Okay, chiral superfields. Okay, so this is SUSY QCD, and the phases of SUSY QCD. This was the subject pioneered by Nani Seiberg in the 90s. Depend sensitively on NF, okay, and boil down to basically 4 different cases. Okay, and it's believed that regular QCD has a similar phase structure, but we still don't know the answer to that. What regular QCD does as a function of NF, because the lattice gauge theory techniques are still not well developed enough. But because of supersymmetry, we're able to actually analyze SUSY QCD without having to put it on a huge supercomputer. Okay, so that's what's so amazing about just this result. Okay, so the phases of SUSY QCD have 4 different cases. If the number of flavors is less than the number of colors, then the dynamics of the theory goes by the name. There's something. Okay, so instantons in this theory generate dynamically, non-perturbatively, generate a superpotential, and I'll be going over in more detail what that looks like. And that's called Affleck-Dine Seiberg superpotential. Okay, actually, if in just SUSY QCD with this number of flavors, this superpotential has a runaway behavior. It looks like this, and so this theory by itself does not have a vacuum. Okay, so and because of non-perturbative effects. So perturbatively, it looks like it has a vacuum, and non-perturbatively, there is no vacuum. So you have to do something extra to this theory in order to get dynamics. Basically, you have to add a potential to the theory which stabilizes this runaway, and then bounds somewhere in between to get SUSY breaking. Okay, so I'll review that. I'll give a quick overview of that in a moment. So if NF is equal to NC, then something totally different happens. Okay, so and physics-wise, what's special about NF equals NC is, so keep in mind this is QCD like, right? QCD has SU3 colors with 3 flavors, right? And so what special thing happens for NF equals NC in these theories is now baryons are possible for the first time. Okay, so before that you can only have mesons, and then now you can have baryons, and so the physics of the theory changes, and you have something what's called quantum modified moduli space. Okay, so you have a moduli space of the theory, which, as we discussed last time, is preserved to all orders in perturbation theory, but when you come to NF equals NC, non-perturbative effects actually modify that moduli space. Okay, so, all right, so people figured out how to build a model of dynamical SUSY breaking using this, and this is called the interligator. The first example of this type is called the interligator Thomas Izawa Yanagida model. Okay, so they wrote the interligator and Thomas and Izawa Yanagida wrote 2 papers at the same time. All right, then we come to the next phase of SUSY QCD, where NF is in this range between NC and 3/2 NC. And here, something really cool happens. So when NF is bigger than NC, you have something called Seiberg duality, okay? And where the theory is actually dual, has a dual description in terms of a totally different theory. Okay, so there's something called electric magnetic duality in this case. And for this range of NF, the dual theory is actually weakly coupled. So this is what's called the free magnetic phase, because the magnetic theory becomes free in the IR. And so together with Ken Trilligator and 90 Seiberg, we showed how to use this for SUSY breaking, dynamical SUSY breaking in 2006. Okay, so it's called ISS. And then the last phase of SUSY QCD is when NF is in this range between 3/2 NC and 3 NC. This is called the conformal window because in this phase, the dual theory is also strongly coupled. Okay, so there's no weakly coupled description of the theory in the conformal window, and so actually nobody has figured out how to do dynamical SUSY breaking yet in the conformal window. Okay, so maybe one of you will figure this out. Okay. All right, so this table summarizes what we're going to discuss. There's a lot to get through in today's lecture, and again, you shouldn't try to understand everything, and I'm not going to prove most things, so it's just going to be sort of a quick tour. All right. So fodder for your reading independently. Okay. Okay, so model, the 3-2 model is the first model we're going to talk about. So this is the 3-2 model is based on the dynamics of SUSY QCD with NF less than NC, and it's the first model of dynamical SUSY breaking that was written down by Affleck, and Seiberg. Okay, so and this is a model with chiral gauge theory. Okay, the 3 and the 2 refer to the 3 and 2 of the standard model. Okay, so this is like it mimics the standard model. It's basically the standard model without hypercharge. And in that sense, you know, we easily get a chiral gauge theory. And so this model has chiral gauge dynamics and evades the Witten index constraint in that way. Okay, so let me write down what the 3-2 model is and then describe how it gets analyzed. So it has 2 gauge groups, SU3 and SU2. Okay, it has the quark fields, and it has a lepton, just the left-handed lepton. Okay, so it's like the standard model with 1 generation and without hypercharge. And so without hypercharge, we don't need to write down the right-handed, electron, right? Because that one only transforms under hypercharge. Okay. So this should look familiar to you, and it's basically we've supersymmetrized part of the standard model. Okay, so let's begin to analyze this model by remembering what the constraints are. Okay, so we have 2 constraints we'd like to satisfy. The first is that the Witten index constraint. So this is a chiral theory. So Witten index is Happy? Okay? And the second thing which we shouldn't forget is this Nelson-Seinberg condition, which says that the model should have an R symmetry in order to break SUSY. Right? That is also a necessary condition for SUSY breaking. So does this model have an R symmetry? So that's actually not a completely trivial question because, it looks like I haven't written down any interactions for the theory, so of course the model has an R symmetry. I could just give whatever R charge I want to these fields, right? There's no superpotential yet, right? So, so it's not a completely trivial question though, because of the following problem, right? The moment I have gauge interactions, I have to worry about something which can invalidate a theory at the quantum level, right? I have to worry about anomalies. Okay, so does the model have an R symmetry? So you have to worry about something called anomalies. So anomalies are a problem that are a constraint on SUSY gauge theories. And the reason, so they're always a constraint, they're always something you have to worry about, for chiral theories at least, because SUSY gauge theories always have fermions in them, okay, because of supersymmetry. Right, so anomalies are a problem for chiral fermions, and SUSY always, anytime you have a chiral superfield, you have chiral fermions. Okay, so anomalies are always present for SUSY gauge theories. Okay, so I don't have time to review how to calculate the anomalies, the mixed anomalies, the gauge global anomalies, etc. in a SUSY gauge theory, so those are in the textbooks. And so all I have time for is to exhibit what the anomaly-free R symmetry is in this theory. Okay, so this is a totally wacky R-charge assignment, which is anomaly-free. And there's also another U1 that I can mix with, a non-R global symmetry that I can mix with, which looks like this. These are the anomaly-free global symmetries. Actually, before I add a superpotential, there's a whole SU2 global symmetry that rotates the right-handed quarks, right? But that's going to be broken the moment I add a superpotential, okay? Which I'm going to do to this theory. Okay. So anyway, this theory is a chiral theory, and it has an R symmetry, anomaly-free R symmetry, Nelson-Seinberg condition. It's also satisfied. Okay, so we'd like to add a superpotential to this theory because otherwise, as I said, it's going to have a runaway potential. So what kind of superpotential can we add? So what constraints should we impose on the superpotential? Obviously, it should be gauge invariant, right? So let's start by listing all the different gauge invariant operators that this theory has. So how do I make a gauge invariant? We all know how to do this. It's a standard model, right? So the independent gauge invariant operators here are basically, well, okay, it's a standard model without the Higgs field, I should say. All right, so it's not quite like the standard model. But the lepton here can look like the Higgs, right? So anyway, so the gauge invariant operators are these two. And there's a third one, which is like that. Okay, so these are the three independent gauge invariant operators that you can make out of these fields. All right, any other gauge invariant operator is going to be a product of some. It's going to be made out of these. Okay, so. Okay, so which of these three should I add to my superpotential? if I want, what other conditions would I like the superpotential to have? So I'd like it to be renormalizable, if at all possible. Right? I'm trying to build a theory of the universe here. So if it could be renormalizable, that would be good. So that selects out these two. Right? So this one's not renormalizable. So these two are both marginal operators. Right? They both have dimension 3. In the superpotential, that would be marginal. Okay, so, and the last thing is we'd like to preserve this R symmetry that we wrote here. Okay, so only one of these preserves the R symmetry. So the condition is that the superpotential should have R charge 2. So let's just go to this table and ask whether Q plus U plus L does the trick, or Q plus D plus L does the trick, and it's the D that I want. Okay, 1 plus 2 minus 3 is 2. Okay, so this one has R equals 2, preserves the R symmetry. Good. So the model that I want to consider is this matter content with this superpotential. And this satisfies the Nelson-Cyber condition and the Chiral constraint. So it has the potential to break Susie's dynamic theory. Okay? Any questions? Yeah.
Why is other renormalizable?
Because it's also preserved by this superpotential. These are literally the only two global symmetries that are preserved by this superpotential. Yeah. So without the superpotential, there's actually a much bigger symmetry here. There's an SU2 global symmetry that rotates U and D. And so this U1 is like some subgroup of that SU2 that's selected by adding this. Also the U1R is preserved, the only thing preserved by this. Okay. Yeah.
You worry about the U1R anomaly because if it were anomalous, then Susie would be restored at one loop, or?
Exactly. Yeah. No, actually, it would be restored. It would be restored non-perturbatively. Yeah. Yeah. The anomaly shows up in the superpotential as a non-perturbative effect. So in these theories, the anomaly shows up as instantons. So there's a connection between the instantons, between non-perturbative effects and anomalies, which pervades all of this subject. Yeah. But yeah, so that's a good question. So the reason we need it to be anomaly-free is that when Nelson and Cyber say, oh, there should be an R symmetry for Susie breaking, they mean like an exact, true R symmetry that's not broken by anything. And if you recall from your quantum field theory class, what is an anomaly, or an anomalous symmetry? It's a symmetry that's explicitly broken, right? It's not a symmetry of the theory, but it only looked like it was a symmetry of the theory, but classically, and then quantum mechanically it's broken. Okay, so that would not satisfy this Nelson and Cyber condition. We really need a true symmetry of the theory. Okay? Good. Okay. Alright, so this is normalizable and it preserves all the conditions that we want. And if you analyze what this does to the theory, so you analyze the potential, scalar potential of the theory, we're not going to have time to do it here, but what you'll find is that this interaction lifts all flat directions. Okay, so the tree level potential that we have here has a nice property that it leads to a scalar potential that grows in every direction. Okay, this theory has many directions, right? The Q, the U, all the scalar fields in this theory are potentially flat directions, or potentially runaway directions, right? And this potential, when you go and analyze it, you can show that it lifts all of the flat directions. Yeah?
Sorry, you don't understand. Is I see that the breaking related not only to perturbative Susie breaking,
Yeah, so we analyzed the R symmetry and this condition in the context of those nonlinear sigma models, right? So no gauge fields. So that's what you're asking, right? And we talked about it all at tree level, right? So that's an excellent question. So why am I talking about the Nelson-Seiberg condition here in the SUSY gauge theory, right? And so the reason is, as we'll see, that so this theory is going to be strongly interacting in the infrared, okay? Just like QCD is. And so things are going to confine, and really I'll be talking about mesons and baryons, gauge invariant singlets of the theory. And it's going to be something like the Carl Lagrangian, okay? And so that is going to be like a linear sigma model, not linear sigma model. Yeah, so you're not going to see the gauge degrees of freedom at low energy because of confinement. Yeah. So that's actually how we're going to analyze this theory.
No, but there was if our symmetry is broken,
yeah.
You say you can tell SUSY breaking.
Yeah.
But I thought it was only important that C-Bateau effects would break SUSY.
Okay, so if this theory didn't have an R symmetry, say it was anomalous, yeah, then there would be an instanton effect, which would add another term to the superpotential, actually. Yeah, so this superpotential is not renormalized at tree level, or not renormalized in perturbation theory, but could be renormalized by instantons. And so when there's an anomaly, then there is actually an instanton effect here. And that's going to come into this Nelson-Seiberg analysis, and we're going to, have the same number of equations as unknowns and all that. Yeah. So that's how that would go. Yeah. So in other words, the anomaly shows up in the superpotential as just another type of explicit breaking of the symmetry. Yeah. Okay. Okay, so that's the tree level behavior of this theory, and so now I want to talk about what happens. So this is the tree picture of it. So what happens non-perturbatively? Okay. So again, to really answer this question, we'd have to spend a lot more time, driving everything. But so let me just sketch though the story. So what happens non-perturbatively? So we should decide. We should first establish. There are two gauge groups here. So we should understand what is the NF for each one. Right. So the NF for SU3. So how many flavors are involved for SU3? Just two, right? There are two flavors, and two fundamentals and two anti-fundamentals. Right? So NF here is equal to 2. And for SU2, the answer is different, right? There's 1, 2, 3. 4 doublets, right? So that's NF equals 2. Okay, so this one has a quantum modified moduli space. If we were to look at this one, the dynamics of this gauge group, and this one has this ADS superpotential. This one has NF less than NC. Okay, but more generally, both of these theories generate dynamically a scale, okay, which I'll denote by lambda 3 and lambda 2, dynamically generated QCD scales, okay? And so, which of these gauge dynamics takes over or dominates depends on whether this scale is bigger or this scale is bigger. Okay? So, if lambda 3 is much, much bigger than lambda 2, okay, that means as I go down in energy, this SU3 dynamics gets strong first, right? So, while this one is still asymptotically free, right? So, if my scales are arranged like this, okay, and I'm going down in energy, okay, then the SU3 dynamics dominates first. Okay, and it's in this limit that we analyze that the 3-2 model does what it does. Okay? So it's when lambda 3 is much, much bigger than lambda 2 that we can ignore the dynamics of SU2, okay, and focus on the dynamics of SU3. Okay? And then what happens here is instantons generate a superpotential. Again, I'd have to spend like an hour at least deriving that, but so I can only tell you the answer. So I'll write it here. So instantons generate a superpotential, which looks like this. Lambda 3 to the 7th power over Q U bar, Q U bar, Q D bar. Okay, so the claim, which I won't prove, is that non-perturbatively in this theory, so this is not normalized, all orders of perturbation theory, yada yada, but non-perturbatively in this theory, this appears, okay, through instanton effects. Okay, so how do we know that this is non-perturbative? Why is this not a non-perturbative effect? It's what? Oh, it's 1 over some field. Well, not quite. No, the reason it's a non-perturbative effect is that it depends on lambda 3, which is a non-perturbative scale. Right, so this lambda 3 is like a QCD scale, so it's like g to the minus 1 over g3 squared. Right? So, because of dimensional transmutation, this scale here can appear, and so the fact that the effect depends on it, or in particular goes to 0, as I send this to 0, it shows us that it's a non-perturbative effect. Okay. So the claim is that this thing should be added to this. Okay, so W full is equal to W tree plus W instanton. Okay, and the way you prove this, I'm not going to prove it, but the way you do it is actually using the same technique of holomorphy that we used before, but the new ingredient is this parameter lambda 3, this dimensionful parameter lambda 3 also transforms under these symmetries, okay? And so we use selection rules applied to lambda 3, and then we can, turns out we can prove this. Okay, so we won't prove that, but let's just look very schematically at what happens to the potential in the presence of this. And as we just observed, this thing has fields in the denominator, right? This thing goes like 1 over the field. So actually, if you sort of analyze the potential that this gives rise to, what you find is that it contributes, this is the runaway behavior of the, sorry, I forgot to say this is called the ADS superpotential. Or it's an example of the ADS superpotential. And it's famous for having this runaway behavior. Right? As I go to the origin of field space, this blows up. And as I go out further and further in field space, this thing goes to 0. So this has runaway behavior, and if I hadn't added the tree-level potential, my theory would have no vacuum. Okay, but in the presence of the tree-level potential, the runaway is balanced by this growing behavior, and I get a minimum in between, which turns out breaks supersymmetry. Okay? One quick way to see that these two together break supersymmetry is, for instance, consider the F-term equation from W tree for L. So dW tree dL is equal to Q d bar, right? So if it were just a tree-level potential and you require supersymmetry, that would force Q d bar to be 0, right? But that would make the instanton superpotential blow up. Okay, so that's why when you balance these two things, you get they balance in a non-supersymmetry, the supersymmetry breaking away. Okay, so and then you can also estimate where this happens. Okay, so let's just estimate parametrically where this minimum occurs. Okay, so this minimum occurs heuristically if I turn off lambda 3. Lambda 3 is the only dimensional thing around, right? This thing has, these are like all the fields, so these all have mass dimension 1. Okay, so just by dimensional analysis, you should go like lambda 3. And how should it depend on this little lambda? So as I turn little lambda off, it's a runaway, right? So this should go like little lambda to some positive power in the denominator. Okay, and then just by, yeah, so we could derive what that power is, but we don't need it. What we do need is, for overall consistency of the theory, so for lambda much, much less than 1, okay, the vevs of all the fields are much, much greater than lambda 3. And this is important, right? This is important because then the vevs of all the fields occur at weak coupling. Or the theory is actually Higgs before it gets to strong coupling. Okay, so these vevs are going to break the SU3. And with a vev which is much bigger than the SU3 confinement scale. Okay, and that is important for the consistency of the theory because it means that this vacuum occurs, for a small lambda at least, it occurs where the theory is weakly coupled, and so our analysis is reliable. Okay, so the analysis is reliable. Okay. So that's a very quick overview of the 3-2 model. Any questions? Yeah, so to really understand this model, this is the crucial aspect, right, is to understand where this instanton generated superpotential comes from. And so that's a very interesting, subject, which I encourage all of you to read about. Okay. All right, so if there are no questions, let me move on and talk about the second model, the ITIY model. All right, so okay, so this is the first model. This was written down by these people, and it's the first model which used massless vector-like matter instead of parallel matter, and used the dynamics of SUSY with NF equals NC. Okay, so the basic version of the model is based on the dynamics of SU2. And so we have some number of quark fields. We have 4 of them. Is anyone confused by this statement? Why don't I have anti-quarks? Why don't I have Qs transforming in anti-fundamental of SU2?
SU2 is real.
Good. They're the same representation for SU2, right? Okay, so for SU2, we actually have an enhanced global symmetry. Usually we would just have SU-NF times SU-NF, but for SU2, we actually have an enhanced global symmetry of SU4, because there's no difference between doublets and anti-doublets. There is one constraint you have to worry about for SU2, something called the Witten anomaly, which maybe you've heard of before, but says that you have to have an even number of doublets in a SUSY gauge theory with SU2. Okay, so I wouldn't be able to do this with 3 doublets, for instance. That theory would be anomalous. Okay, so this theory has SU4, and in order to make it work, I also have to add some singlets to the theory, which transform in the anti-fundamental, in the anti-symmetric tensor representation of the global symmetry. So there are 6 of these. Okay, there are 4 of these. All right, and we're going to rely heavily on a group theory fact that SU4 is completely the same thing as SO6. Okay, so so this is actually a spinner of SO6, and this is just a fundamental of SO6. Okay. This theory has some gauge invariant operators, which we're going to call V, okay, which are made out of the quarks. And we're going to normalize them so they have canonical dimension. Okay, so these are the gauge. So these are not matter fields I'm adding to the theory, but these are derived from this matter content. These are the gauge invariants. These are like mesons. Okay? All right. So this theory has a non-anomalous car symmetry under which the charges look like this. Okay? And so it satisfies the Nelson-Cyber condition, and we can make it satisfy the Witten index if we leave these massless. Okay, so we don't add a mass term for them. And we can explain that by, so these would be the mass terms, these QF times QG. Okay, so we can forbid such mass terms if we impose this global symmetry, SO6, since these transform into the SO6. Okay, so if we impose that as a global symmetry, then the only superpotential we can write down at the normalizable level is lambda S Q, so S FG QF QG. Okay. Which I can also write as a vector of SO6, following way. I mean, I can also write in terms of the vectors of SO6, following way. Okay? So this is the tree-level superpotential that I add to the theory. And the question is now, what happens? What is the vacuum of this theory, this tree-level superpotential? Yeah.
It's the one that's with the F and G.
Okay, good. So this is a flavor index. Okay, so F runs from 1 to 4.
And SU4.
This, yeah. So I'm not writing the gauge index, that's what the dot here is. Okay? But here I'm writing explicitly the flavor index. Okay. So, right, so because this theory has the same number of flavors as colors, it behaves completely differently than the previous model. There's no ADS superpotential, there's no runaway behavior. Instead, there's something called a Kalman modified moduli space. So to understand what that means, we should first understand what the classical moduli space of the theory is. And so that just comes from looking at the superpotential, right, and the F-term constraints. So classically, dw pi equals 0, setting all these things to 0, implies that Q is equal to 0, and S is anything. Okay, so there's a big moduli space, right? SUSY moduli space. And so classically, supersymmetry is not broken, and that's what we want for a model of dynamic SUSY breaking, right? So there's another way to look at this moduli space, which is to first consider what it is without this turned on. First consider what it is without the superpotential turned on. There's still a moduli space for the theory without a superpotential. It's the space of all the gauge invariant operators. Okay, so in terms of the gauge invariant operators, they're in a 6 of SO6. They're this vector B. All right. So the moduli space is parametrized. The moduli space of the gauge theory without the superpotential is parametrized by these B's. Okay. But the B's are subject to a constraint, and the constraint is that B squared is equal to 0. Why is that the constraint? because this is also going to be written as the determinant of this matrix, QF, QG. Okay? And so I'm switching back and forth between SU4 and SO6 language. But anyway, this constraint is really the statement that the determinant of this matrix is 0. Okay? And so why is the determinant of this matrix 0? Classically. It's because QF is, well, so Q I should think of as a 2 by 4 matrix. Okay? Right, this is color, this is the gauge, and this is the global. It's 2 by 4 matrix. So when I multiply them together to make a 4 by 4 matrix, when I multiply two rectangular matrices together, right, that has only rank 2. Or maximal rank 2. It could have rank less than 2 as well. Right? So when I take the determinant of a 4 by 4 matrix with rank 2, I get 0. Right? It's a degenerate. It's a 0 eigenvalue. Okay, so that's the classical constraint, and it looks very nice in terms of SO6 language. Okay, so we're going to use this. Okay, so the space of the moduli space is actually a cone. So this defines a cone, right? And if the superpotential is S times V. Okay, so now we turn on a superpotential. So this is called the B flat moduli space. The moduli space is just the gauge theory. And now we turn on the superpotential, okay? And the equation of motion for S forces V to be 0. Okay, so the equation of motion for S puts us at the origin when W tree is turned on. Okay, so before we turn on the superpotential, we can be anywhere in this cone. After we turn on the superpotential, we have to live right here. Alright, where Q is equal to 0. Okay. Now, the very cool thing that happens in this theory, because it has NF equals MC, is that non-perturbative, the way non-perturbative effects show up in this theory is that this constraint actually gets modified. Alright, so I'm really not doing any of this justice. I mean, so you have to go and like really, to understand that there's a lot involved. Okay, but what happens is that non-perturbatively, the constraint gets modified. And just the fact that, we can say something like that is a miracle of supersymmetry, right? I mean, such statements are completely inaccessible in non-supersymmetric theories. Okay, so geometrically, what this does is it smooths out so this point here is a singular point, okay, where the gauge theory, the gauge fields are, the gauge symmetry is unbroken, okay, and what this does is it smooths it out. Okay, with a width of, order lambda here. Okay, so my moduli space is deformed, especially around the origin. Okay, out here you don't really notice it that much, where V is very large, you don't really notice it. But near the origin, where V is small, this is a big event. Okay, so given that that's what happens, now we see that there is an incompatibility between the constraint, right, which requires V to be non-zero, and the tree-level superpotential, which requires V to be 0. Okay, so the fact that this constraint, that these two are incompatible, leads to dynamic disintegration. Alright, so it's actually fun to analyze that, because as we'll see, well, I don't want to spoil the answer, but an old friend is going to emerge from the dynamics. So the way that this actually breaks SUSY is going to be something we've already seen before. Okay. All right. right, so let me continue analyzing this model. Okay, so let me write it again because it got a little messy over there. So the model is this with a constraint. So it's a constraint. These fields are not free to do whatever they want, but they're constrained to lie on this cone, this deformed cone. Okay. So how do we put together the constraints in this tree-level superpotential? So it turns out that the way to do it is to first solve the constraint and then plug back in. Okay, so let's write the constraint as, so we can solve this constraint by writing b as square root of lambda squared minus little v squared little v. So now this is a vector of SO5. Right, so this automatically now solves the constraint. And then we should also split up S into S naught. So this kind of breaking, so this spontaneously breaks the global symmetry from SO6 to SO5. Which actually is, yeah, so it's sort of reminiscent of what happens in these composite Higgs models, right? Where SO5, you want SO5 spontaneously broken to SO4. So anyway, so we split up S also in SO5 singlet, SO5 vector. And then let's rewrite what the tree-level superpotential is in terms of these. So tree-level superpotential is now S naught times square root of lambda squared times v squared plus S v. Okay. I'm glossing over a bunch of details like what the Kähler potential looks like, etc. So you also have to argue as part of the logic that the Kähler potential is smooth. But we'll be taking that for granted here. So now the next step is to expand around v equals 0. So let's just study the model around the origin. Okay, so when we expand, something nice happens. So when we expand around the origin, something nice happens. And it looks like this. Sorry. Start over. It's not minus a half lambda p squared plus. Okay, so that is the thing expanded out to second order in V. In this little V. Alright, so I promised that we would get back an old friend. Does anyone recognize, is anyone up enough to recognize what this actually is? Maybe not because all the fields have different names, right? This is an O'Rafferty model. In the way we had it before, this was called X, and this was called Phi, and this was called Phi tilde. So if you flip back to your notes, you will find the same model being written with different symbols. Same superpotential, I mean, being written with different symbols. So we recognize an O'Rafferty model where, again, the equation of motion for S naught is that lambda squared, this thing, minus a half lambda v squared should be 0. But then the equation of motion for S is that, so this should be 0, and this should be 0, if the thing is going to be supersymmetric. But you see that they're compatible with each other. Right? That's the O'Rafferty model. Okay, so out of all this non-perturbative dynamics, etc., you see that when we go down to the low energy theory, involving just the gauge invariant operators, we recover a nonlinear sigma model, which breaks SUSY through the O'Rafferty mechanism. So in this way, we see that the two ways of breaking SUSY, namely the tree-level way and the dynamical way, in many cases, well, in this case, are actually the same thing. Okay? So you can have a theory which appears to break SUSY at tree level, but is secretly, has a UV completion as a dynamical SUSY breaking model. And that's what's happening here. Okay, and so we already analyzed what this model does, right? This S0 field is a pseudomodulus. So these other ones are stabilized at tree level. And then S0 is a pseudomodulus. So it's stabilized at one loop at the origin. Right? So we have the S0 being flat at tree level, and then at one loop. In the Coleman-Weinberg potential, it's stabilized at the origin. That was the problem we already solved with the O'Rafferty model. Okay. So in this case, at least, we've seen that dynamical SUSY breaking and tree-level SUSY breaking are the same thing. Okay, and it turns out that it's not an isolated phenomenon, but it appears to be fairly common, actually. Anyway, there are many examples of that. Okay, are there any questions about that? No? Okay. So, for my third trick, I'm going to show you what happens now in this theory here, okay, which relies on, yet again, completely different dynamics. Okay, no questions? So one way to motivate what I'm going to do next is to again consider this Witten index constraint and to ask what happens if we violate it. So far we've considered chiral theories and massless vector theories. Okay, and we were told right that if we study a truly vector-like theory with massive matter, that it's not going to break SUSY. Right? It's going to have supersymmetric ground states. But that still raises the possibility that it could have, so we don't really care necessarily what the ground state of the theory is. We only care about, we could be living in a metastable vacuum. Right? So that allows the possibility, so if you want to have models with metastable vacua, then it motivates you to study these massive vector-like theories, which are often a lot simpler. Okay? So what about vector-like theories? Often much simpler. So in some sense they're sort of more generic. Like for the 3-2 model, you had it was based on a standard model where we sort of already know the answer. But I mean, just viewed on its own, it's a rather cooked up thing, right? The chiral representations have to fit together like a jigsaw puzzle to avoid all the anomalies and all that, right? So these chiral matter models are somewhat contrived, and so it's really interesting to think about, if we just follow our nose and do the simplest possible thing, what are we going to get? Well, that's a vector-like theory, but these have SUSY vacua. And so we should wonder if they could be made, if they also have, in the same theory, metastable vacua. So what about metastable DSP? So can we cook up a theory with this vacuum structure, and then we live here for long enough, So that is what we looked at. And to our surprise, we found that the absolute, pretty much this absolute simplest model you can write down has this behavior. Okay? So that's what I want to show you now. So the model we wrote down is much simpler than what we had before. It's just SUSY QCD with NF flavors. That's the whole model. Okay, so we've gone in a big loop. We've studied all these complicated things, and now we come back to SUSY QCD with NF flavors. And remember, we had an SUNF times SUNF global symmetry before, but this model just has one diagonal global symmetry because we add a superpotential, which is the only thing you can add in such a theory that's normalizable. There's a mass term. Okay, so the claim, this is what we found, is that this model has metastable vacua for m much, much less than lambda. So when the mass is much, much less than the dynamical scale, this model has metastable vacua. Okay. So how did we show this? Oh, I forgot to add, I forgot to say one very important thing. The model only works for NF less than 3 times NC less than NC. Okay, sorry. Yeah, it's not any SUSY QCD model, but it's this in the free magnetic phase. Okay, so how did we show this? Well, the fact that it's in the free magnetic phase is the clue. So we considered what this theory is under Seibert duality. Okay, so before I talk about that, let's first draw a picture of the dynamics of this theory. So this theory has some scale lambda, and I said that we're turning on some mass terms to the theory, much less than lambda. Okay, so, and we're interested in the vacuum of the theory, so we would really like to go to low energy, right? We can answer the question of the vacuum structure if we go to the low energy vector theory. And so what does this theory do, after it hits strong coupling? So according to Seibert duality, what it does is it's described by a completely different weakly coupled, completely different gauge theory, which turns out is infrared free. Okay, so this theory here is asymptotically free, and then you hit the scale lambda, and the magic of Seibert duality is that this maps to another theory, which turns out is infrared free, which means at every energy scale we have a weakly coupled, well, except right here maybe, we have a weakly coupled description of the theory. That's pretty amazing. Okay, if we had that for QCD, well, then whoever found that out would win $1 million, right? Okay, so, so let me write this over here. All right, so what is the Seibert dual theory that describes the dynamics below, that this matches onto below the scale lambda? It turns out it has a different number of colors, SUNF minus NC. It has some things which are magnetic quarks. Okay, and it still has NF of them. And the only other ingredient is a bunch of singlets. So they're gauge singlets, and they transform in, well, they're just NF by NF matrices. Okay? So these are the mesons. And in the dictionary between so this is called the electric theory. This is called the magnetic theory. And in the dictionary between electric and magnetic, there's a map between the mesons of the magnetic theory, well, between these ends of the magnetic theory, and literally the mesons operators of the electric theory. Okay? Okay. So, and then okay, so then the other thing you have to do in the duality is the magnetic superpotential is not quite the tree level one, not quite the electric one, but it's whatever you started with plus a new term, which is dynamically generated, which looks like M QQ tilde. These are all matrices, so we should trace. Okay, so this term here is generated through through the duality. Okay, and this is whatever you started with, expressed in terms of the magnetic theory using this dictionary. So in this case, what it is it's M plus I'm being a little cavalier about dimensions. If you like this should be a dimension 1 canonically normalized field. So I make up the dimensions with a lambda here. Okay, so we define a new parameter mu squared, which is m times lambda. And then there's a mu squared that goes here. Okay, now everything is dimensionally okay. So this is the theory then that we analyzed. So this is what describes the low energy dynamics of this SUSY QCD. Okay, and in this theory, with this number of flavors and this number of colors, is infrared free. Okay, so the fact that there is this gauge group here doesn't really matter. This gauge group behaves like, you know, the electric coupling in the standard model. It becomes more and more free and weakly coupled as you go into the deep IR. Okay, so parametrically, we can just ignore it and just focus on this. It's another West-Amino model. Right, so another model with just parallel superfields. And it turns out this is also an O'Rafferty model in disguise. Okay, that's the miracle here. So, and you can see that actually in an even quicker way than the regular O'Rafferty model. So this is my superpotential. Let's just consider the F-term equations for the ends. Okay, this is mu squared times an NF by NF identity matrix plus Q tilde. Where here I'm contracting the color indices and leaving free the flavor indices. Okay, so let's again consider this is a product of two rectangular matrices. So Q and Q tilde are rectangular matrices which have, say, color in this direction, and in this direction have flavor. Okay? So once again, when I multiply this, together, two of them, what I get is a matrix, an NF by NF matrix, with rank, at most, NF minus NC. Okay, so this thing has rank less than or equal to NF minus NC. So it's impossible to set this to 0. Right? In order for supersymmetry to be unbroken, we would want to set this to 0. And it can't be done, because this has rank at most NF minus NC, whereas this is the identity matrix, full rank. Right? So this is not 0 by what we call the rank condition. Okay, so it's another example of an O'Rafferty-like model, right? Where the F terms of these Carl superfields can't all be set to 0. And again, as in the O'Rafferty model, this is just half of the battle. First we show that all the F terms can't be set to 0, and then you have to check that there's going to be pseudo-moduli, and you have to check that they're stabilized somewhere, that there's no runaway. Okay. So, so you can do that, and you can show that so it's a little more complicated than the regular O'Rafferty model, but you can show that all the pseudo-moduli are stabilized, stabilized. So actually, they're all stabilized at the origin. Okay.
I'm confused though. I thought we were going to find a stable vacuum.
Excellent. Yes. I was hoping somebody would ask that. Okay, so what happened to the SUSY vacuum? What happened to the metastable vacuum? Right. So it looks like we have proven that this model just breaks supersymmetry, right? So it looks like we've gotten too much. Okay. So, right. All right. So let's go. Let's go back to the electric theory. Okay, let me draw again this picture. Here is SUSY QCD. Here is the magnetic theory. Okay, and here I've added the masses. Okay, and I've required that the masses are much less than lambda. All right, so this theory below the scale m, here it's just super Yang Mills again. Okay, so if you like, we start with SUSY QCD. It's still SUSY QCD all the way through, but it's more convenient to talk about it in terms of magnetic theory that's going to be coupled. But then below the scale m, we know that we have to get back to, if you go to well below the scales of everything, you know that you have to get back to super Yang Mills theory. It's going to be very strongly coupled super Yang Mills theory, but it's still going to just be super Yang Mills theory. Okay? And then you know that this theory has some number of vacua, okay, which are described by, so this theory here as NC SUSY vacua. And if you trace it back to the original SUSY QCD theory, which you can using some tricks, you find that they look like this. So the order parameter for the SUSY vacua, for distinguishing between the NC different SUSY vacua, is the meson Feb, and it looks like lambda, well, it's a little more complicated than that, but it looks like lambda disempowered. Okay, if you like, I will write the full formula. Looks like m to the nf, lambda to the 3 nc minus nf, to the 1 over nc power. Okay, so it depends on both m and lambda in this way. And what does this mean? Okay, so what does this mean? So when we analyze this O'Rafferty model here, we're really studying the theory near the origin, near m equals 0. Okay, so these m's are like the pseudo-moduli, and if I were to draw the picture of the potential for the ends, very roughly speaking, it would look like this at tree level, right? And it would look like this at one loop. That's in another example of this O'Rafferty model thing. Okay, but in any case, we're studying this O'Rafferty model near the origin, where the scale here is set by lambda. Okay. If on the other hand you look at where the SUSY vacua occur, and you take care of the dimensions and stuff, they actually occur much bigger than lambda. Okay, so here's what the SUSY vacua occurs. And so you simply can't see the SUSY vacua by analyzing this theory. This is an example actually of something we talked about in an earlier lecture when somebody asked, if you're studying only an effective theory, do you have to worry, does that get you all the vacua? And I said, well, that might miss some vacua that are bigger than the cutoff, right? might miss some beds that are bigger than the cutoff. And actually, this is a prime example of that, because this is actually an effective theory, even though it's normalizable. It's an effective theory valid below this cutoff lambda. Okay, and then these vacua, these SUSY vacua occur beyond that cutoff. Okay, which you can see. Well, you can see in this effective theory, but you have to work harder. You have to take into account some non-perturbative effects. Okay. But it's easier to see this in the electric theory, the theory above the cutoff. Okay, so right, so that's the full picture of this, the potential in this model. Here you have metastable SUSY breaking, and here you have some number of discrete SUSY vectors. Okay. There's one more perspective you can have on this theory, actually, which I shouldn't have erased that. Okay, so let me just mention it. So the crude magnetic theory has is this theory that becomes more and more weakly coupled in the IR, and well, okay, so let me. Oh, I have it here actually. Okay, so this superpotential. I think this is like an. So okay, let's do a consistency check. Right. So this is a Rafferty-like model which breaks SUSY. So by the Nelson-Cyber condition, it should have an R symmetry. Right? And it clearly does. I give the M's R charge 2, and I give the Q tilde R charge 0. Okay, so it satisfies Nelson-Cyber, but it's not that simple because there is this SU NF minus NC magnetic gauge group. Okay, so if this were just a Weston-Newton model with no gauge interactions, then it would break SUSY and there would be no metastability. But there is this weakly coupled gauge symmetry here. Okay, and it turns out that the R's charge of 0 being assigned to these magnetic quarks is anomalous. So there is an R symmetry here, but it's anomalous. All right. If you like, it's an accidental R symmetry. Right. It's going to be broken by higher dimension operators, including the one that influenced the anomaly. All right. So there is an accidental. So the magnetic theory has an accidental approximate R symmetry. And if you go back to what we were saying before, that accidental approximate, the fact that it's approximate is connected to the metastable vacuum, the fact that there's a metastable vacuum, right? So the R symmetry is explicitly broken by instantons, by the anomaly, and that restores SUSY, and that's where this comes from. Okay, but the fact that it's approximate, so there's a small parameter that makes this a better and better R symmetry. What is that small parameter? It's the gauge coupling here. Okay, so this gauge coupling being weaker and weaker makes this a better and better R symmetry, right? Because it's only the gauge interactions that break the R symmetry for the anomaly. Okay, so the fact that this is approximate gives you a small parameter, if you like, which controls the separation between these two, and which you can control the lifetime. Okay. All right. So I have 5 minutes left, but I think maybe I went through all this too quickly. So let me just quickly. Maybe I should just summarize. Okay. So just to summarize. We've seen a few examples of dynamical SUSY breaking, rather fast, I admit, which rely on different phases of SUSY QCD. Okay, and each phase has its own subtleties and its whole subject. In fact, these phases are not separate from each other, and that's how one way that cyber was able to derive all of this is they're actually all related by a web of normalization group flow. In other words, so this is like going down in a number of flavors, right? So I can go from this phase to this phase by integrating out some quarks. So I'm adding masses for some quarks and integrating them out, right? So all of these are tied together by normalization group evolution, by different flows. Okay, I can also reduce the number of colors by Higgsing some, by introducing some Higgs fields and Higgsing this, okay? So really this is all, these phases are all connected to each other, and to study it, it's, that's a complete endeavor. But then they all find applications in different models of dynamical SUSY breaking. And the last thing is that we saw that, at least in 2 of the 3 cases, okay, that because of duality, essentially, that in the low energy description of these theories, in the chiral Lagrangian, if you like, that the SUSY breaking, even though it's dynamical SUSY breaking, actually looks like it comes from an Arachne model. Okay, so that actually motivates the study of Arachne models, generalized Arachne models, in their own right. One challenge is that neither of these, both of these Arachne models were the like variants on the basic one that we studied. And in particular, both of them have vacua at the origin. Okay, just through the way that the one-loop Holman group works, both of these examples were stabilized at the origin. Why is that a problem? Because what is it the origin of? It's the origin of this field that has R charge 2. Okay, and so if it's stabilized at the origin, that means that the R symmetry is not broken. Okay, not broken. Even though SUSY is broken, the R symmetry is not spontaneously broken. And why do we need R symmetry breaking again? Yeah, so you're not going to get gaugino masses in this theory on its own because the R symmetry is unbroken in the vacuum. Well, because there is an R symmetry and it's unbroken in the vacuum. And maybe you can get some mileage out of the fact that it's explicitly broken by the anomaly, but often that turns out to be too small for the gaugino masses. So that drove a lot of model building too, is ways to modify these theories to get the R symmetry broken, and because of the gaugino masses. Okay, so I guess I should stop here, and feel free to ask me more questions.